Good evening. So I told you about the change in the way I want to evaluate partial differential equations and Fourier series last lecture. I summarized that discussion in the syllabus. So if you go under first of all exam 2, it's going to be only 3 problems and 80 minutes covering only module 4. And if you go under the course grade distribution, you will see a mini project appearing for 5%, and the exam 2 is being reduced to 15%. That makes the total contribution of exams 20 plus 15 plus 20, which is 55%, which is what the optional comprehensive final will also be worth. Of course, I'll make some tweaks to also this, which I'm still thinking about. I'll get back to you on that. Okay. And if you go under project 1 description, there are instructions to submit by 5:30 p.m. on October 30th. And then there is a mini project based on DFT, which describes the problem and tells you what to do and to submit also this. Actually, this should be November 11th. Okay. So this mini project is going to be due by November 11th, which is 1 week after the exam 2. Okay. So your October, hopefully you would spend with project 1. Your November, you would spend on both mini project and project 2. Okay, so that makes sense. I'll try to look over the syllabus once again to make sure I don't have any kind of inconsistencies like this, if especially about the submission date and so on. So if you find anything that is a little bit confusing, please feel free to ask me. Okay. All right. That said, we'll get back to the next module on partial differential equations, which is covered in chapter 12 of the textbook. Okay. So, of course, as engineers and people that have taken courses on various topics like solid mechanics, fluid mechanics, heat transfer, control systems, you do know that partial differential equations appear in many places that are used to model physical situations. They are the result of the application of fundamental laws of physics to a particular context. And what we are going to learn in this particular unit is a technique called separation of variables. We are going to apply this technique repeatedly for every type of partial differential equation. And we are going to see specifically a few types. The first type is called the heat or diffusion equation, which in Cartesian form and in one dimension is written as partial u over partial t equals c squared partial u over partial x squared, where c is a real number. And the second type of equation we are going to see is the wave equation. Second derivative with respect to time is equal to c squared second derivative with respect to space. We are also going to see what is called as Laplace equation, which is usually partial u over partial x squared plus partial u over partial y squared equal to 0 in two-dimensional Cartesian. How do you end up with these equations is something I am kind of making you learn by doing your own project. That is what the project is supposed to teach you. How do you do mathematical modeling? What we are going to go through in class are solutions to these template equations, which may occur in your modeling problems, and you can use these techniques to solve them. Okay. We'll start with Cartesian, but we also plan to cover cylindrical, or polar coordinates as well as spherical polar coordinates. We'll also do those in addition to Cartesian. Okay, so it's a lot of same concept applied to different geometric systems. Okay. So we'll start with the wave equation to demonstrate the idea of separation of variables, which you write partial u over partial time equals c squared partial u over partial x squared. C is a real number called the wave speed. This equation is a model for wave propagation in an one-dimensional medium. Something like an infinite bar in every direction. That is a bar which is infinite in two directions, and you are interested in the wave propagation along one of the directions, which we call x. And this equation describes the wave propagation, let's say, between two planes in that medium, which are situated at x equal to 0 and x equal to L. As it is a equation that involves partial derivative with respect to time and space, we need to specify initial conditions which are specified throughout the computational domain or throughout the domain of propagation, and the domain being 0 less than x less than L. So we need to specify what is u of x when time is 0 and what is u partial u of partial t of x at time 0. These two are initial conditions. So we can give them some random symbol. We can call this f of x and we can call this g of x. Like saying when time is 0, what was the initial position and displacement, or initial position and velocity of that medium. Okay. We also need to specify boundary conditions that is at one of the boundaries, which is x equal to 0, we need to specify what is the value at all times. Okay. And at the other boundary x equal to L, we need to do the same. So I should say boundary conditions at x equal to 0 and x equal to L. These two pieces of information are required if we were to get a solution that is specific to a given problem. If I just give you this equation and ask you to solve it in some domain without telling you initial and boundary conditions, you will just stop with general solution. If you want a particular solution, you need to know what are the initial and boundary conditions. Okay. So as far as boundary conditions are concerned, they need to be specified at the boundaries x equal to 0 and x equal to L. If the value of the function is given at both locations, those are called Dirichlet boundary conditions. If just the value of the function is given at both the points, since this is one dimension, this represents this point and this point represents the boundary of the domain. So instead of the actual value of the function, if the slope of the function were given at x equal to 0 and time, this would be called a Neumann boundary conditions. A Neumann boundary condition that is specifying the function itself is called Dirichlet, specifying the slope is called Neumann. And in any given problem, these combinations are possible. You could have a Dirichlet condition on one side and also on the other side. You could have a Neumann condition on one side and on the other side, and vice versa. You could have D and N. But typically, specifying slope on both sides is physically sometimes unrealistic because it won't constrain the value of the function itself. When we do some examples, I'll try to explain why this is usually not the case. You need to have at least one value of the function in order to obtain a solution. Until so far, whatever I have said is nothing to do with this technique called separation of variables. All I told you is we have a PDE which has both time and spatial dependence. There is initial and boundary conditions. You could be a CFD expert. You could discretize this and solve it. That would make this a numerical solution. But what we are specifically seeking in this unit is obtaining series solutions of PDEs, and the technique we use for that is called separation of variables. That is why this unit connects heavily with what we saw in the previous unit. So what is this separation of variables? It starts with a simple idea that the solution u of x comma t is the product of two functions, each of which is a function of x only and time only. This is the idea. We are essentially going to repeat applying this idea for every type of PDE, and it will work for any linear PDE involving time and spatial coordinates, which could be r theta p or r theta c. It will work for any linear PDE, but to start at some point which is easy to grasp, we'll start with the wave equation. So if you say the solution is a product of two functions, then substituting this solution into the wave equation, we would get the second derivative with respect to x of the function x multiplied by g equal to c squared times f of x times the second derivative with respect to time. I'm just substituting here u equals f times g. Is there, if you have any question or some confusion, not sure how we got this from the wave equation, please let me know. I just skipped a step, assuming you would just not find that to be a problem. Are we good? Are we okay?
C is a constant, that's why you are writing it.
C is a constant. It's a wave speed. It's usually a positive number, which we just assume it's just a given number, something that comes from measurement or area. Are we okay?
Left side is the derivative with respect to time.
Oh, okay. So I swapped it. So I should write.
But as you said, C is a constant, so still it is.
No, I don't want to say that. I want to retain that form. So the left side is this equal to c squared, second derivative with respect to space times g. Thank you. So we can do some rearrangement to write g double dot divided by g equal to c squared f double dash divided by f. I mean, this is the steps, the standard steps under separation of variables. This will apply for all the equations that we will later see. Okay. So we'll say this is equal to some constant k, okay, and the value of k is to be determined. We'll just say this ratio of g double dot over g is equal to c squared times f double dash over f is equal to some constant k, which we don't know yet. K can be a negative number, positive number, but one thing we will say is k is going to be a real number. Wait, not necessarily, sorry. K is to be determined, it could be complex as well. K will be a constant, but it could assume different values. It's not like a spatial variable, it could assume multiple values, but each value is a constant, which could be real or complex. So what we have gotten ourselves is, instead of a PDE, we now have two ordinary differential equations. So you can write G double dot minus K times G equal to 0 and F double dash minus K over C squared times F equal to 0. Actually, they bring the C squared along with this G to write A C squared G equal to 0 and F double dash minus KF equal to 0. So constraining K as a real number and considering the possibility that K could be positive and K could be negative. These are the two possibilities if we say K is to be a real number. Suppose K is positive, we'll call K equal to some mu squared. Okay. K equal to mu squared. You can see already where this is going because you already learned about ODE solutions. This will imply F double dashed minus mu squared F equal to 0, whose characteristic solution or whose general solution would look like f of x equal to C1 e power mu x plus C2 e power minus mu x. Would you agree with me? Right? Just if mu is a positive number, it has to have an exponential solution. The problem with these exponential solutions is, can you see the problem? Do you see the problem? Mu is a real number which will what make k to be a positive number. If you have C1 e power mu x and C2 e power minus mu x, more often than not, this solution has the potential to be infinity for some value of mu. That is, most physical solutions will not have exponential dependence in space simply because that would mean at some point the amplitude of your function is going to become infinite. So this is typically some type of solution which is incompatible with physical boundary conditions. I'll tell you why. You have, let's say, a rope and you constrain it at both the ends, x equal to 0 and x equal to L. Suppose two of you are holding the rope at each end. So you will say the value of displacement here is 0, assuming both the people are strong enough to hold it in place. U is 0 here and U is 0 here, which means that wave or that rope can have only amplitudes which are finite. If you model this wave propagation and your solution predicts that at this point the wave has infinite amplitude, that's just physically not realizable. So we rarely consider these solutions. I would say rarely, not like never. Okay. The other possibility where we write k is a negative number equal to minus p squared, where p itself is a real number, that would lead to f double prime plus p squared f equal to 0. This would mean f of x is equal to a. I just want to use the same notation as the book. A cos px plus b sin px. We also saw this in the first unit or second unit. So these are finite valued functions that can represent physical quantities. So very often we go for solutions that are in terms of trigonometric functions. Okay. So we have f of x equal to a cos px plus b sin px, where we still don't know what p is. P is to be still determined. Okay. Can I erase this? All right. So now if you want to figure out A and B, we need to know boundary conditions. Need to know boundary conditions. That is, you need to know what is U at x equal to 0 for all time and what is U at x equal to L for all time. And since x equal to 0 and x equal to L are just points, it has to be some finite value. And for simplicity, we'll start with 0. The value of U of 0, comma t and U of L, comma t need to be constants which we take to be 0 for simplicity. So we have, this implies f of x equal to 0 and g of t equal to 0 and f of x equal to L times g of t equal to 0, which simply implies f of 0 is 0 and f of L is also 0. If you make a different choice here, or if you are dealing with a problem in which, suppose you are not dealing with waves, suppose you are dealing with a physical quantity like temperature, like a heat wave, okay, like alternating values. In that case, it could be finite value, but you know the procedure, you can come back here and revise your calculation. So f of 0 is 0, which implies a times 1 plus b times 0 is 0, and f of L is a cos PL plus b sin PL equal to 0. The first equation implies a is 0, and the second equation implies that this product is 0, and we have to assume b is non-zero to avoid a trivial solution of f of x equal to 0. So if we assume that sin PL is 0, or PL has to be an integer multiple of pi, where n runs from 0, 1, 2, and so on up to infinity. Actually, not 0, because that would include trivial solution from 1. So that implies P, the parameter, is n pi over L, where L is the length of your domain. So your solution is f of x equal to sine, actually I should write P sine n pi over L times x. And n is a parameter which can take values of 1, 2, 3, and so on, all integer values, positive integer values. So you are going to get a solution. If you take n equal to 1, your f of x can be b sine pi x over L. If you take f equal to 2 or 3, sorry, n equals 2 or 3, sine 2 pi x over L. Now, what do you know about sine functions? If I take sine n pi x over L, what can I say about it based on what we learned about orthogonal functions? If I say fn of x is sine n pi x over L, is fn of x orthogonal? How do you prove orthogonality or disprove? So you can consider the integral 0 to L, the domain of interest, fn of x times fm of x dx, and if this is 0 for m not equal to n, that proves that this is orthogonal, and if it's finite value, otherwise. You've done this problem before. You do know that this function is orthogonal. So that was the last unit when you proved orthogonality or checked for orthogonality. So what if a function is orthogonal? What does it qualify it for? Louder, please.
Okay, basis.
It could serve as a basis function when you say sine n pi x over L and n can take integer values. That means this has many solutions, all of which can be solutions to the original ODE. Original ODE, which is this one. So you could write the function f of x is summation n equals 1 to infinity dn times sine n pi x over L, where Bn is the corresponding amplitude for each value of n. Remember when we wrote orthogonal series, we wrote f of x equal to summation m equal to 0 to infinity am ym. We have already excluded n equal to 0, so the indexing starts at 1, and this is basically Bn here is am here, and ym here is sine n pi x over L. This may look very simple now, but the reason I want to enforce this now is because when we do cylindrical or spherical polar, it can get pretty complicated. So you want to be able to follow the thread. That's why take your time and let's get this right. Okay. So f of x can be written, or fn of x can be written Bn sine n pi x over L, and f of x itself can be written as an infinite series n equals 1 to infinity Bn sine n pi x over L. We have to figure out what are Bn's, right? We haven't done that yet. So we'll leave it like this for a minute and go over here and see what's happening. G double dot minus kc squared g equal to 0, and we are going in with k equals minus p squared, which is minus n squared pi squared over L squared. So this implies G double dot minus n squared pi squared c squared over L squared G equal to 0. Sorry, I have a negative sign here, so I should have a positive. And this combination of symbols, I'll call it omega squared. Omega equals n pi c over L. C is usually a wave speed, which has units of say meter per second, and length is meters, which gives you a pure number, which gives you a frequency. So this is essentially n pi times frequency. So we can write G double dot plus omega squared G equal to 0, which implies G of t is symbol that they use. So we'll use our own symbol. We'll write C cos omega t plus D sine omega t. Of course, omega is, you recall, is n squared pi squared c squared over L squared. So I'll add a subscript n to denote that there are multiple frequencies, each for a value, each for n equals 1, 2, and so on.
I thought.
And they just square these things for the S versus for the sphere. If we scale.
Actually, would be simpler to write omega n is n pi c over f. So I would have, I'll rewrite this G as Gn of t equals Cn cos omega n times t plus Dn sine omega n times t. So this notation and this notation is to signify that different or that multiple basis functions are possible by varying n. So coming back to the function u of x comma t, which we said could be f of x times g of t. We are now recognizing that fn of x times gn of x, gn of t is a valid basis function for a chosen n. Fn gn is a valid basis function, which means u of x comma t is really an infinite series, n equals 1 to infinity, un of x comma t, which is n equals 1 to infinity, fn of x times gn of t. So when I wrote this, I didn't again ask you the question, is this function orthogonal or not, so that it can serve as a basis function. Obviously it can, because we just established that sine is an orthogonal function. We already know that cosine is also orthogonal. So that question is, we didn't have to raise it again. So this you would write is equal to summation n equals 1 to infinity. What is fn of x? Bn sine n pi x over L. And what is gn of t? That is Cn cos omega n of omega n times t plus Dn sine omega n times t. So I can write this as see, this is Bn times Cn and this is Bn times Dn. They are all arbitrary constants. what you can club B and C together and call it a single symbol. Club B and D together and give it another symbol. You don't need to have three constants. Okay. So we'll erase this. We'll write sine n pi x over L times. Now I'll converge with the book and write Bn cos omega n times t plus Bn star sine omega n times t. Each of these functions, that is each value of n, generates a function that is a product of space and time functions. Each of these is called an eigenfunction. Okay, and the omega n values are called eigenfrequencies. The set of omega n values, omega 1, omega 2, and so on, is called the spectrum. Okay, we have come this far. We did assume a boundary condition. That is, we said u of 0, comma t equal to 0, u of L, comma t equal to 0. These were boundary conditions. That helped us reduce from 4 arbitrary constants, 2 for space and 2 for time, to only 2 arbitrary constants. To get the remaining 2, we need initial conditions. You would agree with that, right? So if we have initial conditions, we can figure out the last 2 boundary conditions. Okay. So initial conditions, we'll write u at x comma 0 is something that is, this is initial, I'll call it f of x. This is initial displacement, if u represents displacement. And partial derivative of u with respect to time at x comma 0, we'll call it g of x. This is initial velocity. So in the example I mentioned about 2 people holding the rope at both ends, this represents the fact that they are holding it at the ends. This initial displacement is, suppose a third person comes to the center of something, lifts the rope up to some height, and then lets go. That would be the initial displacement. The initial deflection they gave to the rope is f of x. If they just let go without giving it any additional momentum, we could say the initial velocity is 0, because all they did was just leave it. It just fell naturally due to gravity. That making sense? Like physically, how this would tie in with a modeling problem. Okay. So let's just assume in general f of x and g of x are given as some known functions of x. Could be constant, linear, quadratic, 0, something. F of x and g of x are considered to be known. With that, with your knowledge of Fourier series, how would you figure out Bn and Bn star? You know the answer, you just don't want to say. Yes, please.
Legendary how the question is called.
Sorry,
How legendary is called.
why legend is called? Anyone else? What's the next step? What would you do?
Just find the Fourier transform technology, having the EN coefficients with a Fourier transform.
So by Fourier transform, you mean writing a formula with integral of f of x.
Yes.
Okay. So what he said as Fourier transform can also be physically written as, you know what is u of 0 comma t. Sorry, u of x at time 0. That is f of x. Initial displacement. Just take the right hand side, substitute t equal to 0. So when you substitute time equal to 0, this sine term goes away. You are left with cos 0, which is just 1. So this is nothing but infinite series, n equals 1 to infinity, sine n pi x over L times Bn. If this is what Bn is, we can write Bn equal to 1 over L, 0 to L, f of x sine n pi x over L dx. F of x is nothing but initial displacement. If it's an exam situation, it's provided. If it's your lab or your research or your work, it's something perhaps you would measure or control. So it's known either way. They get this limits and all correct. 2 over L. And similarly, if we write the partial derivative with respect to time at x and t equal to 0 is given to be g of x, the initial velocity. This is infinite series, n equals 1 to infinity. Derivative of u with respect to time. So cosine becomes sine, and sine 0 is 0, so you don't have to worry about Bn. This is Bn times omega n cos omega t. So this is going to be Bn star omega n cos 0, which I won't write, times sine n pi x over L. So if you want to get here, so this is my function u of x. I have to take the derivative with respect to time, which will be wave speed. So this is unaffected. This is the derivative of cos is sine. Sine is cos. So sine at time 0 will be 0. So this term goes away. Bn times cos of time, and I have to substitute t equal to 0. Only Bn star remains. But I also have to multiply by omega n. So by the same logic, using the idea of Fourier transforms or Fourier series, Bn star equal to 1 over omega n times 2 over L, 0 to L, g of x sine n pi x over L dx. You observe here, if u is a displacement, Bn also has the same unit as u. So it should have same unit as u, inverse length. So that, wait, yeah, so you have a length here. That is f of x is a displacement, so it should have units of length. And L also has units of length. which will make Bn unitless. Okay, that checks out. Bn star, okay, Bn star here. What is the unit of Bn star? This is 1 over frequency as unit of inverse time times length. Okay, meter per second. That is the unit of Bn star is inverse of meter per second. And over here you have g of x, which has meter per second, which together makes Bn star also unitless. Okay. All right. So this is you have now figured out what is Bn and Bn star. That is, if I gave you functional forms for f and g, you will be able to do the integration and complete the problem. Okay. So the final solution would be, if I rewrite this, sine n pi x over L, Bn, which is now known, times cos omega n times t plus Bn star sine omega n times t. When you do your projects, you'll hopefully teach me about modes and superposition, getting standing waves, or getting the solution to be the sum of waves. That is something I leave you to do later. Now, if you look at how to practice or practice problems, if you look at problems 5 to 13, problems 5 to 13 of problem set 12.3. Problem set 12.3, problems 5 to 13. They have already assumed this type of a boundary condition. They are saying the 1D wave equation is used to model the displacement of a string with L equal to 1, and C squared equal to 1. They didn't say which unit. Let's just say L equals 1 and C squared equal to 1. They also say the velocity is 0, which is g of x equal to 0, and f of x is the only non-zero value function. So if g of x is 0, automatically you can get Bn star will be 0. So your solution is essentially a product of cosine and sine, with Bn being non-zero and coming from this integration. And the type of functions they have given for f of x include sine 3 pi x, some trigonometric functions. If you look at problem 9, which we will try now, problem 9 talks about a waveform 0 to L equals 1, and here is L divided by 2. It talks about a triangle which goes up to 0.1 and then comes back to 0. So this is the initial displacement f of x. So how would we represent this as a function? It is a piecewise function, which is continuous but not differentiable at L divided by. It has the same value, but the slopes are different, so it's not differentiable. So we can write f of x equal to, right, this is c times x over L for 0 less than x less than L divided by 2. What would be c? So 0.1 equals c times L divided by 2 divided by L, which will make c equals 0.2, right? 0.2. And what would you write about this? I mean, for my dumb brain, I'll just write f of x minus 0.1 divided by 0 minus 0.1 equal to x minus 0.5 divided by 1 minus 0.5. Right? Like if you are in an exam scenario, this is a sure shot thing, but if you could do this faster, good for you. So you can do write f of x equal to minus 0.1, 0.5. So this is minus 1 by 5 times x minus half plus 0.1, which you can simplify further, I'm sure. So this is like writing 0.2 minus or 0.2 times 1 minus x. 0.2 times 1 minus x over L. For L divided by 2 square. Or if you want this even a little bit clutter free, you can call this 0.1, which will just make this 2c. Then you can later at the last step substitute c equals 0. So by now you are very clear about how you would do Fourier series or evaluate the necessary integral to get Bn based on this f of x. Right here. So this is one variant of a question where you have an initial displacement but no initial velocity. Initial displacement without initial velocity. If you look at problems 14 onwards, actually just problem 14, not onwards, there you have non-zero initial velocity. So in that problem, you have an initial displacement which is 0. So f of x happens to be 0, that is u of x comma t equal to 0 happens to be 0. And the first derivative of u with respect to time at time 0 happens to be g of x, which is given to be a triangular velocity, pretty much like what we had there, equal to 0.01 x for 0 less than x less than pi and 0.01 times pi minus x, pi less than x less than 2 pi. No, actually 0 to pi by 2 and pi by 2 to pi. So here you have non-zero initial velocity with the zero displacement. These are the two variants we can think of. Also remember that we started with fixed at both ends. So when it comes to modeling real problems, you have to convert phrases into mathematical statements. So when you start saying the rope is fixed at both ends, that statement translates into math as displacement is zero. And initial velocity, which is zero, g of x equal to zero. And if in our example, if we had, for example, suppose we had a rope held at both ends, we took a series of pins and gave the initial displacement not just like a triangle, but some kind of a polynomial which is bounded between two ends. And then you remove the pin at time zero, that would be your funky initial condition. So you can be creative about this. Okay. So what I expect you to be practicing is try a variation of boundary conditions. You can challenge yourself with different combinations. What if you have, for example, at one end it is fixed, but at the other end, instead of being fixed, the slope is specified. Partial u over partial x is a constant, and you have the slope to be specified. And the initial displacement or velocity, let's say initial displacement is non-zero and initial velocity is zero. So if we do something like this, where you have this to be zero and this to be a slope, where it would change? It would change in the very first step when we said f of zero is zero, and instead of saying f of L equal to zero, we would say f dash of L equal to constant. From there on, the derivation takes a different trajectory, but the ideas all remain same. I'm not going to actually solve the entire problem, which I expect you to try. Okay. What I want to cover is one more PDE that is similar to this, but has a slightly different form called the heat equation. So that you have two of the common equations, at least like you're familiar with.
Yeah, in the exam, the problem will be related to this family of equation.
Yes. In fact, the exam will have only three problems. I'll tell you right now, one of them is a Cartesian problem, one of them is a polar or cylindrical problem, one of them is spherical. And some combination of boundary conditions of these. Very simple to say, but it's like, there are only limited things I could ask. That's what I'm trying to say. Okay. 1D unsteady heat or diffusion equation. That's what the usual name is, which is written as partial derivative with respect to time equal to c squared second derivative with respect to space. I'm not going into the derivation of these, but I'll just mention a model for diffusive processes like heat conduction or mass transfer. So we'll have a domain, let's say, that goes from x equal to 0 and x equal to L. Could be a problem, something like this represents a wall or a window. Let's say this is a window. And the inside x equal to 0 is exposed to the indoor environment. And this is the wall thickness or the window thickness. And x equal to L represents the exterior. So the temperature here, let's say, is like, what's today's temperature? 80 degrees Fahrenheit, let's say. And indoor is, say, kept at 70 degrees Fahrenheit. How will the heat propagate, or how will the temperature distribution evolve is the question. Okay. So to solve this, you need boundary conditions which should specify U at both ends, x equal to L at time, or you could have partial U over partial X at either of the ends. So what is like setting the value of the function? That is like setting the temperature, whereas setting the slope could represent setting the heat flux. Now, experimentally, you know this, setting a heat flux is much easier than setting temperature. When you boil something on the stove, are you setting temperature or heat flux? Heat flux, right? Because you set the burner at a certain rate. You know what your fuel is, propane, butane, whatever it is. It's going to combust and release heat. And if the combustion is steady, the heat flux into your vessel is going to be steady. So it's a constant heat flux boundary condition, which is experimentally easier. But in terms of calculations, that will be a slightly more involved one than specifying temperature. If you were to specify temperature in a heat transfer experiment, what would you do? What would you need to do? I want to hold this indoor at 70 Fahrenheit. What do I need to do? You are the control systems guy, right? Say something. Sorry?
Keep on expecting the heat from the.
Well, you want to maintain temperature. So if you are suppose, yeah.
Cross feedback to Torres, we keep it.
You need to have a feedback loop so that you can vary the heat flux suitably to hold it at a certain temperature. The heat flux has to modulate the changes that are going on to hold it at a constant value. If you specify heat flux, depending on what medium it is, at what rate the heat is removed, you're going to have some temperature that is going to come out of your solution. So in other words, mathematically speaking, when I'm setting temperature or a Dirichlet boundary condition, I'm telling you the value of the function at both ends. But when I'm specifying the slope or the flux, I'm only telling the way in which the function has to terminate, that is the slope of the function, but it could terminate at this level or at 0 or at some other value. Only the slope is specified, which means the value of U at that boundary point has to come from the solution. Right? This is something. It's a very minor nuance that you have to notice, that you have to compute the value of U here. Suppose one of your problems could be, if a heat flux is maintained at one of the walls, find the resulting temperature. So you'll have to get the solution and substitute x equal to L in order to get that temperature. It's like a one step extra. All right, good. Can you tell me what to do next? Like, separation of variables, the same procedure can be applied again. Oh, wait, sorry. So I talked about boundary conditions, which could be Dirichlet or Neumann. So usually there has to be at least one Dirichlet boundary condition. You can't constrain both the ends with only heat flux. It's like saying, I'll put a heater here I'll put a heater here and supply heat into the material from both sides, that's untenable. At some point, the material is going to fail. Right? So one of them has to be a temperature boundary condition. If you were to get a finite valued solution that is mathematically making sense. Okay, what about initial conditions? You have a time derivative. Say something about the initial condition. Is it needed, not needed? Is it matter, does it matter, doesn't matter, something? Sorry? Only one initial, or not even only one, you have to specifically say, you need to know the temperature profile in the domain at time 0, when your solution begins. So if you write a spatial variable x and a time variable t, this is x equal to 0, t equal to 0. So it is unlike your wave propagation problem, where you needed two boundary conditions because of the way the differential equation comes out. Here you need one, and that only one has to be specified at the start of your propagation, which gives a sense of time. So then the problem is defined for positive time. And very soon we'll find the initial temperature profile that you assume at time 0 usually has no bearing on the final solution, especially the steady state solution. You'll see why. Okay. So u of x at t comma 0 needs to be known or assumed. If you are interested only in the steady state solution, that is, if you are interested in t equal to infinity only, which means you can just assume any u of x comma t equal to 0 can be assumed. If you want to get u as a function of time, to understand unsteady heat transfer or the time rate of change, then u of x comma t needs to be known. Needs to be known or measured. All good. We have 10 minutes. So to solve this also, we are going to start with separation of variables by assuming u is a product of one function x and another function of t only. So that's going to give us partial u over partial t is f times g dot, and partial second derivative with respect to x is f double dash times g, which together will give us fg dot equal to c squared f double prime times g. So we will rewrite this g dot divided by c squared g equal to f double prime divided by f. The reason we write it as c squared is to denote it is a positive number and c is a real number, which in practice c squared is called diffusion constant or thermal conductivity. C squared. We'll say this is some k, and obviously we are not interested in negative values of k because that would lead to exponential solutions in space, which can't be physical. So we'll write directly minus p squared. So you end up with again f double prime plus p squared f equal to 0, same as last time. This has not changed. And with a boundary condition that looks like f of 0 equal to 0 and f of L equal to some constant. Actually, the book goes for both being 0. It's like saying you have a domain in which u is 0 at both ends. Okay. That is, it's like having a block exposed to the same temperature on both ends, because since temperature is relative, you can zero it. And then you give it an initial temperature profile and then ask how the temperature will evolve over time. That's the whole essence of heat equation, is to compute the time evolution or the unsteady dynamics. This is one possible use. That is, you might have something that is between fixed levels and ask to resolve the time difference. The other case is, if you have x equal to 0 at a certain temperature, I'll call it UA, and the other end at another temperature UB. How does this temperature profile get set up? So you will have an evolution. Initially, the temperature is, let's say, 0 everywhere, or let's say it is just UB everywhere. Slowly, that temperature will start developing. How does it develop? The solution comes from heat equation. So in this particular equation, you can expect both type of boundary conditions, especially if you're doing modeling. You are more likely to end up with these type of finite valued boundary conditions, which you can define u star equals u minus ua. So this will become u star is 0, and this is u star equals ub minus ua. So you can somewhat simplify the problem. Okay. I'll stop with this one remark to say you have g dot plus p squared g equal to 0, which leads to g of t equals exponent of minus p squared t squared. In the wave equation situation, g of t was a cosine and sine or a trigonometric function, whereas here it's a decaying exponent. P squared is a positive number. You have a decaying exponent. Okay. So most transient solutions or most solutions to the heat equation will have a functional form that scales with e power minus p squared t times sine n pi x over L or plus cos n pi x over L. Or in other words, you have what is called as a decaying trigonometric wave or decaying trigonometric functions. The actual derivation isn't at all complicated. It's exactly like a repeat of what we did for wave equation, which is given in page 558 to 561. Page 558 to 561. Please go through the derivation. All I'm doing in this unit is giving you toolkits for you to select a problem that is, say, wave propagation or diffusion or unsteady diffusion. I'm teaching you how to solve each type of equation. What you select is your choice. That's what the project is about. Okay. Of course, I will look at your selection, approve it before you start working on it, so that what I've had in the very first time I taught the course is somehow that batch of students all selected really interesting problems. I still have slides from that semester, but in the next time I offered the same project, somehow all the students came up with like 1D Cartesian problems and they said, this is what I could come up with. So the challenge or the complexity was very poor, which I did not like. So this time I want to ensure that you select at least problems that are appropriate for this course, this level. Okay, so to wrap up, if you go to problem set 12.6, problems 5 to 17 typically talk about the 1D heat equation with various combinations of boundary conditions. So I would definitely ask you to try those. Okay. So in the next lecture, I want to start discussing the two-dimensional Laplace equation in Cartesian. So this is our next target. Okay, so this is set under section 12.78 or 12.6. Okay, thank you.